So for section 6.1, we're going to be looking at factors. And factors, if you think about it, are what make up a number. So this word also means stuff outside of math class. If I say, like, what are factors for being in this class? And you said, well, I need it for my major. I need it to get my degree. So those are kind of the reasons, or they're that make up why you're in this class, why you're at this college. You say, I want a career that is going to require this level of degree. I don't want to do the job that doesn't require this degree. So those are all factors or reasons that make up the whole reason you're here taking this class or other classes. Well, in math, it's kind of the same way. We're looking up what numbers make up 12, specifically through multiplication. So a couple ways of doing this. If I want factors of 12, I could break it apart, doing what's called a factor tree. And I could say, what multiplies to make 12? Well, it's even, so we could do 2 and 6. By the way, you could also have said 3 and 4. There's nothing wrong with that. But I recommend if you do the tree that you don't just break apart the 6 and put another 2 and 3, that you bring down the other 2. Okay? And what this is called prime factorization. Why? Every number that's there cannot be factored any further. They're broken down as far as they can. So the prime factorization of 12 would be 2 times 2 times 3, or you could write it as 2 twice, or 2 squared, times 3. Okay? So that would be the prime factorization of that number. We do the factor tree. If I ask you to list all the factors, and this is actually probably the skill that we'll use the most, we would do what's called a T-table. Okay? It's called a T-table because it's shaped like a T. And you start by listing factors of 12. The smallest factor, the smallest whole number that goes into 12 is 1. And what you do is you match it with 1 times what makes 12. And after 1, I check 2. And 2 times 6 makes 12. And after 2, I check 3. And 3 times 4 makes 12. And after 3, I check 4. But we already checked 4, so I'm done. Anything bigger would have matched with anything smaller. So in this situation, this is not the prime factorization, because these numbers are not all prime. This is the way that we would list all factors of 12. So our factors would be 1, 2, 3, 4, 6, and 12. If I want the greatest common factor, then I'm going to list all of the factors that they have, and I'm going to figure out what they have in common. So I could take 12, and we said that was 1, 2, 3, 4, 6, 12. And I could do the same thing with 8. So I'll do the 8 over here. And that would be 1 and 8, 2, 4, 3 doesn't go in, 4 does. We're done. We got anything bigger with anything smaller. So for 8, we have 1, 2, 4, and 8. And if I look at these lists of factors, they have 1 and 2 in common and 4 in common. So what is the greatest factor they have in common? Well, 4. Or, if you like the table, the tree, remember we broke this apart. The 12 was 2 times 2 times 3. 8 is 2 times 4, or 2 times 2 times 2. What you do is you can say, what do they have in common? Well, they have a 2 in common. In fact, they have 2 2s in common, right? All the ballerinas here get excited. What do those 2 2s make? So they have 2 times 2, 2 times 2 in common. So if I take what they have in common and multiply it, that also will give me the greatest common factor. So I can list out the factors and find the largest one they have in common, or I could do a tree and just grab everything, all the terms they have in common, multiply them together, and that's everything they have in common, the greatest common factor. Let's kick it up a notch. Now, I don't feel like listing all the factors of 72. 1, 2, 3, 4, 6. It's not going to be fun. So this is one where I would definitely try the tree. I would say, well, 72 is what? 2 times 36. 36 I can break apart as 6 times 6. Some people will leave this 2 and then just come back at it later. That's actually kind of a bad habit. I would encourage you to bring the 2 down. I find people are more successful with that. One reason is because currently, if I multiply 2 times 36, I'm still get 72. if I don't bring this 2 down, this line does not equal 72 anymore. It would just be the 36. So by bringing the 2 down, every line still equals 72. So when I break apart the 6 as 2 times 3, and the other one as 2 times 3, by bringing the 2 down, if I were to multiply all these numbers, they would still equal 72. Okay? 120, I see it ends in a 0, so I'm like in 10 times 12. You could have also done 2 or 4 or 6, there's a lot of options there. 10 would be 5 and 2, 12 would be 4 and 3. I'm not done, because I can still break apart the 4, and then I would bring everything down. And 432, okie doke. Well, I'm going to try 8, and so this is where I encourage you to have a calculator. But 8 does go in there, what is that, 54 times, I believe. Okay, so then the 8, I'm going to break apart as 4 times 2. Will a 4 go in there? No, unfortunately not. But a 9 does, so I'm going to go ahead and do 9 times 6. The 4 is 2 times 2. Bring down the 2. 9 is 3 times 3. 6 is 3 times 2. So what is the greatest common factor of all 3 of these numbers? Well, what do they have in common? This has 2 2s, 2 2s, 2 2s. In fact, I think they all have 3 2s. Okay, this one has more, but I need them to be in common. It looks like they all have at least 1 3. So there's a 3 there, a 3 there, 3 there. This one has 2, but this one does not. So I think that's it. So 3 2s and a 3. So our greatest common factor, everything they have in common, is basically 2 times 2 times 2 times 3, 8 times 3, or 24. Try this one. Greatest common factor, 15 is what? 5 times 3. 30 is 3 times 10. 3 times 5 times 2. 90 is what? 9 times 10. 3 times 3 times 5 times 2. What do they have in common? Well, they all have a 3. This one has more, but I need it to be in common. They all have a 5. And that's it. So the greatest common factor is 15. See, sometimes people are like, oh, what do I do? All this one's got use. Well, that means 15. That number actually goes into both of them. The greatest common factor of 15, 30, and 90 is 15. 15 goes into 30, 15 goes into 15, and 15 goes into 90. What do we do if there's variables? Panic, right? No. All right. So we're going to start with the greatest common factor of the numbers. And the good news is the numbers are a lot nicer. 6, 9, and 12. Okay? I could just go what goes into 6, 9, and 12, and the largest one they have in common is 3. You could totally do that. Let's go ahead and say 3 times 2, 3 times 3, 3 times 4, 3 times 2 times 2. So what do they have in common? They all have a 3. And that's it. They don't all have anything else in common. So the greatest common factor here is going to be 3. And the lowest power of any common variable. They have a common letter, don't they? This one has 4 m's, this one has 2, and this one has 5. So why don't I keep all 5? Well, they don't all have 5, right? This one has 4 of them. This one has 2 of them. And this one has 5 freaking m's, right? So the question is, how many do they have in common? That's why we keep the lowest power of that common term, 3m squared. So what do we do with this? We're not just doing this for fun and giggles. When I look at this, we're going to start factoring, okay? I guess not yet. Negative 12p to the 5th. Negative 18, q to the 4th p. What is negative 12? I recommend pulling out the negative 1 times about 2 times 6. So then negative 1 times 2 times 3 times 2. 18 is going to be negative 1 times about 9 times 2. That's still negative 18. So negative 1 times 3 times 3 times 2. What do these have in common? Well, they have a negative 1 in common. They have a 3 in common. And they have a 2 in common. Now you may look at 12 and 18 and go, yeah, the largest number that can go into them is 6. Awesome, that's fine. I'm just showing you a technique you can use. So what do they have in common? A negative 1 times 2 times 3, or a negative 6. What else do they have in common? Well, they have some p's in common. But they don't have 5 in common. Really, all they have is 1 in common. What about the q's? Here I got all these q's over here, right? Well, do they have that in common? So when I look for the greatest common factor, it has to be what they have in common. Onward. Let's see. 6y to the fourth is e squared. 9, oh mess. Let's start with 6, 9, and 2. 6 is 3 times 2. 9 is 3 times 3. And 2 is already prime, just 2. So what do they all have in common? Nothing. Technically, that means they are all divisible by 1. You don't have to write the 1 there, but that is basically the greatest number that goes into 6, 9, and 2 in common. These are all technically times 1. So the only thing they have in common is the 1. Okay. Start with the letters now. Y to the fourth, y to the sixth, ruh-roh. There's no y's. So when I'm looking for a common, there won't be any y's in common here. When I look at the z's, z squared, z to the 8th, z to the 9th, what do I keep? How many do they have in common? And that would be the greatest common factor of those three. Okay? So what are we going to be doing with this? Well, we're going to be factoring. See, factoring is basically, and if we could take 3 times x plus 6 and make it 3x plus 18, it's basically going the opposite direction. Rather than multiplying the 3, I basically take out, or I divide out, what they have in common, and it goes on the outside, and I end up with 3 times x plus 6. So I write this because if you can distribute, and you can think backwards, and you can factor, okay? It's I've even had people. I had one student tell another student, it's reverse distributing. Rather than multiplying stuff in, we're taking stuff out. We're taking out what they have in common. Okay. So when I have 4x squared plus 6x, start with 4 and 6. What do they have in common? Well, they are both divisible by 2. You could break them apart, but that is the greatest common factor of the number 4 and 6. They're both divisible by 2, not by 3, not by 4, nothing bigger. 2 is the biggest. And what about the x? Well, they do have an x in common. How many? We factor out the 1x. So now that that is the greatest common factor that we pulled out, we have to figure out what's left in this group. Okay? So if I've divided out the 2 from the 4, I'm left with a 2. I divided out an x, so instead of x squared, that is x to the first. I divided out the 2 from the 6, so that leaves that as a 3. And I divided out that x, so that x is gone. This is one way of thinking about it. If you like, we're basically dividing this out of both of those. Another way of thinking about it is to check your answer by distributing. 2x times what gives me 4x squared? Well, 2 times 2 gives me 4. X times x gives me x squared. 2 times what gives me the 6? It has to be a 3. And this has an x. A lot of people will put another x here. And that doesn't work, because if you just check it, you would end up with 6, x times x, x squared. So that you cannot have that x there. Please be careful with that. Another common mistake is people go, well, look, I just pulled out an x from both of these. Why isn't this x squared? I go, well, just like I pulled out a 2 from both of them and it wasn't 4. You pull out what they have in common. The greatest common factor goes on the outside. And then you figure out what's left, and that goes on the inside. Let's kick it up a notch. 8, 16, and 12 are all divisible by, somebody's going to tell me 2. And that doesn't bother me too much, because look what we're going to be left with. A 4 an 8, and a 6. So 2 is not wrong as far as you did find something in common, but 4, 8, and 6 are still divisible by 2, so we could have taken out something bigger. You go, okay, instead of the 2, what if I pulled out a 4? That would make that a 2, that a 4, and that a minus 3. 2, 4, and minus 3 now have nothing else in common, so that was the greatest common factor. What do we do with the letters? Start with the p's. 5, 6, and 4. How many can we pull out? Well, how many do they have in common? The lowest exponent of that, which is p to the 4th. What's left? Well, this had 5. I pulled out 4. That leaves us with 1. This had 6. We pulled out 4. That leaves us with 2. This had 4. We pulled out all 4. That leaves us with no more p's. If you want to put that, that doesn't hurt my feelings, but that's unnecessary. The p's are pulled out. So all 4 of these p's got factored out there. Okay? Q's, we've got squared, third, and fourth. So the lowest they have in common would be q squared. This one, we pulled all of them out, so it's gone. This one, I pulled 2 out, left us with 1. This one, I pulled 2 out, left us with 2. And this is factored completely. What about fractions? Right? Can you do this? We got 1/3 and 2/3. It's really not as crazy as you think. What you do is you do the greatest common factor of the numerator and the greatest common factor of the denominator. So when I look at this, the numerator is 1 and 2. That's not terribly exciting. They're both divisible by 1. Over the denominator is a 3 and a 3. So what's the greatest thing I can divide out of 3 and 3? How about the 3? I need to leave some more space because I got letters. I got b squared and b. So they both have how many b's in common? So now I need to think about a couple ways of thinking about it. I pulled out the 1 and the 3, so the 1 and the 3 are gone. And I pulled out a b, so I'm left with a b. Another way of thinking about it is 1/3 b times what gives me 1/3 b squared. 1/3 times, if you put a 1 here, it does not hurt my feelings. I'm not going to, but it's not wrong. 1/3 times 1 gives me 1/3, and b times b gives me b squared. Minus, how about on the top? 1 times what gives me that 2? Well, that needs to be the 2. 3 times what gives me that 3? If you make that 2 over 1, that does not hurt my feelings. Technically, I just need the 2. What about the b? Well, there was a b. We pulled it out, so there are no b's left. This is factored completely. Factor out the top, factor out the bottom. Double check that 1/3 times minus 2 gives me minus 2/3. So, like I said, if you're really struggling with that and you wrote this as 1/3 times 1b, that would be fine. Minus if you did 1/3 times 2 over 1. I would clean it up on the left as it looks a little cleaner, but the right is also correct. I have no problem with that at all. Okay, 14, 21, and 7 are all divisible by. If you're not sure, 14 is only divisible by 7 and 2. Well, 2 won't go into 21, 2 won't go into 7, but they are all divisible by 7. The A's, they all have 3, 2, and 1, so they have 1 in common. The B's, they all have 2, 3, and 1, so 1 in common. This will not be full credit. Technically, you are still factoring out what they have in common, but as a general rule, and this is going to come in really handy in the next section, if the leading coefficient, if the first number is negative, then we factor that negative out. It's easier to leave everything positive, okay? Two ways of thinking about this. Negative 14, pulled out negative 7, that left me with positive 2. That didn't make sense to me. Well, it makes sense to me, but if it didn't make sense to you, negative 7 times what makes negative 14? A couple ways of thinking about it. We had 3 A's, pulled out 1, left us with 2. We had 2 b's, pulled out 1, left us with 1. Here's where I'm going to catch people, because 7 times what makes that 21? A lot of people will put plus 3. But negative 7 times positive 3 does not make positive 21. When you pulled out the negative, everything changes signs. So that 21 becomes a negative 3. Double check, negative 7 times negative 3 is positive 21. We pulled out an A, left us with an A. We pulled out a B, left us with 2 B's. And last but not least, negative 7 from 7 leaves us with negative 1. Check it this way. Negative 7 times what makes a positive 7? And we pulled out both the A and the B, so we are done. Factored it completely. Same thing on example 10. 8, 16, and 4. A lot of people will think the largest thing you can pull out of those is 2. You're like, that's what I was thinking. But everything that's left is still divisible by 2. So you should have pulled out a 4. I hope some of you are screaming at your screen right now, because what did we just say? If the leading coefficient is negative, factor it out, so that this becomes a positive 2, this becomes a negative 4, this becomes a positive 1. Everything changes signs. Tell me about the x's. Leave enough space. How many in common? The lowest power is x squared. If I pull out 2 from the first one, that leaves me with x squared. Pull out 2 from the second, that leaves me with an x. Pull out 2 from the last one, and they're all gone. You are now factoring. Let's keep going. This last part, we have 2 terms. We have 2 groups. I will have some people try to multiply all this in. You're making your life harder than it needs to be. I see 2 groups, and they have something in common. What do they have in common? Well, this entire group. So what I can do is I can actually pull out that group that they have in common, which is A plus 3. And what am I left with after I pull that out is A plus 4. We can check this. You don't just have to believe me. Some of you are like, I don't know, it seems like math magic to me. Well, if I were to distribute this all out, this would become A squared plus 3A plus 4A plus 12. So how about A squared plus 7A plus 12, right? What about this if I were to distribute this? A squared plus 4A plus 3A plus 12. That is A squared plus 7A plus 12. They are the same. This is factored out completely. So just like you can take out terms, you can take out groups that they have in common. This last one, x squared x plus 1 minus 5 times x plus 1, what do they have in common? Factor out the group. What's left when I pull that out of both of them? This seems bizarre, because why would I ever want to do this? I'm about to show you, okay? We're going to do what's called factoring by grouping. It's going to basically make questions that are difficult to factor easier. And this is, I believe, our last topic here. So the idea is this. When I have 4 terms, I can change example 13 back into example 12 or 11 by grouping the first 2 terms and the last 2 terms and factoring out like terms from each group. So the 2x plus 6, they have what in common? Plus ax plus 3a. What do they have in common? Well, they both have a. I just went from 4 terms, 1, 2, 3, 4, to 2 terms, 2 groups. Why would I want to do that? Those 2 groups now have what in common? So now, like we did on example 12, I can factor out the group that they have in common, and I'm left with 2 plus a. By the way, a lot of people, when their teachers teach this to them, for some reason, they put the 2 plus a first, and then they put the group at the end. This is just fine. Doesn't hurt my feelings at all. Okay? So goofy smile, if you want to do it that way, it's a little weird to me, but it's not wrong. There's nothing mathematically wrong with that. Okay? I encourage you again, you could check this answer. X times 2 would give me 2x. X times a would give me ax. 3 times 2 would give me 6. And 3 times a would give me 3a. That's all the same 4 as we started with at the beginning. So this is factored completely. 4 terms. Big hint, factor by, group the first 2, group the second 2. Now this is weird because it's got a negative. So here's what I encourage you to do. Make this plus a negative 3 and then group the negative with it. Minus 3 is the same thing as plus negative 3, but you want to group that negative with the 3. And a lot of people, if they don't do that, will make this plus sign disappear. Things start getting weird. Don't do that. Make it plus negative 3, group the negative there. Okay? First group has what in common? Well, t to the third t squared has t squared in common, leaving us with t plus 2. Second group has 1 in common. 3 and 6 are both divisible by 3. Here's the issue. We're going to end up with negative t minus 2. We didn't follow our directions from before. What did we say? If the leading coefficient is negative, then we should factor out that negative. Not that it's wrong to do it the other way, but when you do it this way, now that t is positive, and now that 2 is also positive. So when the leading coefficient's negative, even if it's in our group here, factor it out. What's the whole point of going from 4 terms to 2 terms? These have what in common? Times t squared minus 3. Last example. 4 terms. Factor the first 2. Factor the second 2. It's minus x, so we make it. First 2 have what in common? Second 2 have 1 in common. Minus x plus 3? I will have some people, first of all, if the leading coefficient's negative, we said we're going to factor that out, so we're going to factor out a negative. But what about a number? What do 1 and 3 have in common? Well, 1. I strongly suggest you put the 1 there. It's not wrong if you don't, but I strongly suggest you do, because what will happen is when we factor out the group x minus 3, if you don't have that 1 there, people will just go, oh, it's just x squared. But it's not. It's x squared minus 1. And that is factoring by grouping. Our next factoring method is going to be if I have a trinomial and I want to factor it. They call this guess and check. I like to call this a logic approach. And so what I'm going to do is I'm going to start with something that's already factored. We're going to distribute it, and then we're going to undistribute it. We're going to do the opposite, which is basically to factor. So when I distribute this, okay, we multiply the m with the m. We get m squared, m times 7, 7m, 2 times m, 2m, and 2 times 7, 14, right? And then we add them together and we get m squared plus 9m plus 14. So now that this has been distributed, how do we undistribute it? How do we factor it? How do we go backwards on this? Well, I do this in 3 steps. First, I look at the m squared. Second, I look at the c term at the end. And last, I check. First, where did that m squared come from? Well, we got it by multiplying m times m. So make your 2 groups and say what multiplies to make that ax squared. Well, m times m makes m squared. Second, we're halfway there. All I need is these two numbers, right? Well, what do these two numbers do? Well, these two numbers multiply to make that c at the end. So we go, what multiplies to make c? What multiplies to make 14? Well, worst case scenario, I got a t-table for that. What multiplies to make 14 is 1n, 14, 2n, 7, 3 doesn't go in, 4 doesn't go in, 5 doesn't go in, 6 doesn't go in. This is it. These are all the factors that multiply to make 14. And then they make that 9. How do we get that 9? We added the 2 and the 7. So basically you say, what of these, all these numbers that multiply to make 14, which of these will combine to make that 9? Well, the 2 and the 7. And to make a positive 14, they'd have to both be positive. And to make a positive 9, they'd have to both be positive. Is this right? Yeah, I know it's right. You could always check it, right? You could always take it and distribute it. You can do kind of an AC on this. I think it gets a little more complicated, but you can say, if you like your x's, you could say 1 times 7 is 7. The middle number was the b is the 9. And so you can kind of answer what two numbers multiply to make the 7 and combine. Am I doing that right? 8 times. I'm messing up already. Sorry. So a, excuse me, was the 1n squared, c was 14, and b was the 9. Okay. So AC would be 14. In the middle will be 9, and you go, what two numbers multiply to make 14, combine to make the 9, 2 and 7. And then what you do, and I, once again, you've got your answers, 2 and 7. You could go straight to the group and write it. Or you could fill it in the box, go x squared, split the 2x and the 7x. And then you could literally kind of factor by grouping. X squared and 2x have x in common. X times x would give us x squared, right? X times what would give me that 2x? X times what would give me the 7x? I messed up here. That should be a 14 at the end. Sorry, the C. X times what would give me 7x? And so I have x plus 2 times x plus 7 gives me, well, it should have been m, but x squared plus 9x plus 14. Okay, so there are lots of options. I like to just do the guess and check on this, but if you're comfortable with a big X, then use the X method. Some people call it X box, some people call that diamond method, and there's all kinds of methods. You can also use our area models. You take those two numbers and fill them in. I'm going to keep approaching it with the logic model, but I want to encourage you that if you have a method that works, you feel free to check it with me. As long as it works and it's mathematically sound, feel free to keep using that method. So, like when we get to this one, you go ahead and if you've got a method and it's different than mine, work it out and see if you get the same answer as me. And if you're not sure, raise your hand. Okay? But here's what I see. Logically, what multiplies to make x squared is x times x. What multiplies to make 20 combines to make 9. I could list those using a t-table. 1 and 20, 2 and 10, 4 and 5. How am I getting the 9 there? I'm thinking 4 and 5. But remember, I need it to not just combine to make a 9. I need it to combine to make a negative 9, which means I need that 4 and that 5 to be a negative. That's how I would approach it. That to me is a logic approach. You could use this AC or this X method where I go 1 times 20 is 20. The B is minus 9. Two numbers that multiply to make 20 combine to make 9, 5 and 4. They'd have to both be negative. And then you could take those two numbers and fill it in. So there's choices, right? Or, if you really like to, take it up a notch. You could take that AC, that 5 and 4, and put it in the area model and factor out what each one has in common. X times x to make x squared, x times minus 5, x times minus 4. So we have x minus 5 times x minus 4. So you got some options here, okay? I like the kind of guess and check method or the logic approach. I don't mind the x. You're going what multiplies to make the AC, what combines to make the B. It's a nice way of organizing your thought process, but I can do that mostly in my head. So you got choices here, okay? I'm going to say that for me, I'm sorry, on this next one, I would have no problem, once again, doing it logically, but I'm going to go ahead and put the AC. So what is 1 times 32? And the B is negative 12. Two numbers that multiply to make 32 combine to make 12. 1 and 32, 2 and 16, 4 and 8, 5, 6, 7, I think that's it. If you're not sure, once again, there's a tool we can use for that. 3 doesn't go in, but 4 does. 5 doesn't go in, 6 doesn't go in, 7 doesn't go in. This is it. Somebody's like, I already see the 12. But to make a negative 12, to combine to make a negative 12, both the 4 and 8 would need to be negative. So I can use those two numbers, and I can say my answer is, excuse me, t times t minus 4 and minus 8. Check it, is it right? We can always check these. That's why I love this chapter, because if you think it's correct, take your second and just check it. T times t is t squared. T times negative 8 would be minus 8t. Minus 4 times t would be minus 4t. And negative 4 times negative 8 would be positive 32. Combine the like terms, we get t squared minus 12t plus 32, which is what we thought we would start off with. Factoring. Okay? Y squared minus 8y minus 9. A lot of people, if they do this logically, will think this doesn't factors, because here's what they'll do. First, they'll look at the y squared and go, what multiplies to make y squared? Right? Second, they'll look at the 9 and they'll go, well, what multiplies to make 9 combines to make 8? They're like, there's nothing there because 9 is only 3 times 3. That is not true, though. Because if I look at the 9 on my table, 9 is definitely 3 times 3, but it is also 1 times 9. So that's where that tool can come in handy, that t-table, because a lot of people forget that 1 times 9 is still 9, and 1 and 9 can make a negative 8. If the 1 were a positive 1, and the 9 were a negative 9. Once again, if you prefer, you would put the negative 9, the negative 8, still have the positive 1, the negative 9, and get that answer. Different methods, different approaches. Always know that you can check it. Y times y times negative 9, 1 times y, and 1 times negative 9. And this turns back into y squared minus 8y minus 9. What if things get all crazy? We got like x to the 5th. People are like, oh my gosh, this is crazy. Well, always look for like terms first. I got a 4, a 28, and a 40. Those are all divisible by 4. What about the x's? Well, 5, 4, and 3, they have 3 in common. What does that leave us with? 4 times 1, x squared, 4 times minus 7, x, and 4 times 10, no x's. What we have left here is a trinomial that can be factored, go from 3 terms to 2 groups. Once again, I'm going to do my logic approach. First, what makes x squared? Second, what multiplies to make 10 combines to make 7? How about 2 and 5? But check, for it to make a negative 7, the 2 and 5 would need to both be negative. This is not our answer. You must also bring down 4x to the 3rd for it to be completely factored. Couple more. Negative 3x to the 4th, positive 15x to the 3rd, minus 18x squared. Oh, buddy. I definitely see 3, 15, and 8 are all divisible by 3. But if that's all you see, you're going to get yourself in trouble, because this is way easier to factor. if the x squared that's left is positive, which is why we what? If the leading coefficient is, we factor out the negative with the 3. And we factor out how many x's in common. And that leaves us with a positive x squared, a negative 5x, and, I messed that up, 3 times 5, okay, and a minus, or positive 6. Okay, when the leading coefficient's negative, factor out that negative. 6 is one of those examples where I catch a lot of people, because I'll have people do this logically, and they'll do x times x, 6 times 1, negative 6 plus 1. And they go, look, first, it makes x squared. Second, 6 times 1 is 6. Third, that combines to make a negative 5. What's the issue with this? Well, negative 6 times positive 1 is not positive 6. See, 6 can make 5 one of two ways. 1 and 6 can make 5, or 2 and 3. So the 6 and 1 don't work this time, but I could use a minus 2 and a minus 3 to make that negative 5, and check that the negative times a negative would make that a positive 6. Remember, this is not your final answer. Don't forget to bring down the like terms that we factored at the beginning. Last but not least, what do they have in common? 2, 6, and 2 are all divisible by. And p third, p second, p to the first, they all have a p in common. Leaves us with 2 times 1, p squared, 2 times 3, and a p. And a lot of people will do this, and it's wrong, because 2p times nothing does not give me 2p. It's 2 times 1. Please catch that. That is a common mistake. What are you going to do from here? You got choices. You can put the 1, the 3, try to find some factors. Okay, you can do it logically. P times p is p squared. What multiplies to make 1 is only 1 times 1. How am I going to make a 3 with that? 1 and 1 doesn't make 3, does it? This is all you can do this time. Our final answer would be 2p times p squared plus 3p plus 1, because that trinomial that's there does not factor any further. 1 times 1 does not make 3. Okay, so this is not factorable any further. Now notice our answer is not that it's not factorable, because we did factor out like terms. So, and I don't know, I might take a quarter point off for that depending on my mood, but just be careful, because I'll have people pull out the like terms and then go, this is not factorable. I go, you were contradicting yourself. You just factored something out and then called it not factorable. You factored out like terms. What was left was not factored. So now this is factored completely. Okay. So that should be it. This should be a pretty easy kind of couple sections. Get to work on them, and I will see you guys soon. For section 6.3, there's a couple ways of approaching this. You can still factor if you have something a little more complicated logically. The problem is it really starts getting more complicated as the numbers get bigger. But I'm going to start with that, because there are a lot of people that really just will continue to factor these logically. They'll kind of put the blood, sweat, and tears in it. So logically, here's the idea. If I look at this first, I say, well, what can multiply to make 6r squared? The problem here is that there's two options. It could be 6r and r, or 3r or 2r. So you actually have to consider both, and you have to kind of guess and check the numbers in there until you can find something that makes that r in the middle. Okay. So second, I still look at the 1. What multiplies to make 1? Well, it has to be 1 and 1. And when I go to check it, I go, all right, this is going to obviously give me my 6r squared, but this is going to give me 6r and 1r. And can that 6r and 1r make a 1r in the middle? No. Then this didn't work. And if there were more options besides 1 and 1, we then have to check those and switch those. And this is where this kind of guess and check method really starts to stink, because it can create a lot of work. But look down here, once again, 3r and 2r can also make 6r squared. So we try the 1 and the 1 there. And when I check that out, obviously that's 6r squared still. But now I have 3r and 2r. 3r and 2r could make 1r if that 2 were negative and the 3 were positive. So 3 times positive 1 and negative 1 times 2. And now this would actually work. Okay, so this would be our factored answer. You can still guess and check, but like I said, it gets a little more complicated. Sometimes you may have, 10, 15, upwards of 20 different things you have to check. This one only had a couple, but got some options. So what I'm going to do is I'm going to show you another method. It's just really a beautiful way of handling this and kind of structuring it. It's called factoring by grouping, or it's called AC factoring. Okay, and what you do is you take the A and the C, 6 times negative 1, and you put a negative 6 up there. And then we take the B, the 1 in the middle, and put it down there. And we do this like we did before, where we say what multiplies to make 6 combines to make 1. Well, that would be a 3 and a 2. And to make a positive 1, the 3 would need to be positive, the 2 would need to be negative. What we do is, these used to be our answers. Like we would just go, oh, this is easy. It's just r plus 3 and r minus 2. That's not right this time, because r times r would not give us 6r squared. So we can't just go straight to doing that. What we do instead is we use these two numbers to split up that r. So r is the same thing as 3r minus 2r. And here's where you got to stop, and we need to make sure we agree. Is 3r minus 2r still 1r? Okay, we haven't done anything except just kind of break this apart. So now instead of having 3 terms, we have 4 terms. Why would I ever want to have 4 terms with a polynomial here? Factoring by grouping. See, I can group the first 2. What do the first 2 have in common? A 3 and an r, leaving us with r plus 1. What do the second 2 have in common? Well, negative 2r minus 1, not really divisible by anything in common, but we said this before, if the leading coefficient's negative, factor out the negative 1, leaving us with, it looks like I divided the last one wrong, 2r plus 1. I'm going to go back and fix this. Hopefully you caught me already. 3 times 1 is not 6. If I factor out the 3r, that leaves us with 2r plus 1. Okay? So this is cool because we've gone from 4 terms to factoring by grouping. These two have something in common. 2r plus 1 times 3r minus 1. What do I like about this? I didn't have to guess or check anything. It's a really nice way of dealing with this. Plus, you may have to, like I said, sometimes if you're guessing and checking, you may have 10, 15 options, and maybe none of them work. And so you have to check all 15 before you decide if something's not factorable. Here, if I use this process right, and I fill in these numbers, if there aren't 2 numbers here, then this is not factorable, and I saved myself a lot of work. So I'm going to keep emphasizing this factoring by grouping. Really a vital skill. Factoring is going to be the foundation for Math 51, so you need to make sure you get strong in this skill. All right, let's try this again. 12z squared minus 5z minus 2. Just for fun and giggles, I'm going to say, so what if I didn't like this whole factoring by grouping? You would have to go, first, what makes 12z squared? Well, that could be 12z and 1z. That could be 3z and 4z. That could be 6z and 2. Do you see where this is going to start getting ridiculous? And then I'd have to check 2 and 1, and if that didn't work, I'd have to check 1 and 2, 2 and 1, and 1 and 2. So I'm looking at 2, 4, 6 different things I may have to guess and check before I might find the answer. That's assuming it's even factorable. I hope you are getting the idea that the guess and check really has its limitations. An easier approach is this AC. See, what is 12 times negative 2? How about negative 24, and the b term is minus 5. I'm looking for two things, what multiplies to make that AC and combines to make the b. Well, 24 is 1 and 24, 2 and 12, 3 and 8, ding, ding, ding. 3 and 8 can make a negative 5 if the 3 is positive and the 8 is negative. The only weird thing about this is you got to figure out what am I going to do with those two numbers? That's step 2. We're going to split the bx. We're going to split the middle term using these two numbers. So that negative 5z becomes positive 3z minus 8z. Why would I want to do that? Well, what did we just do, right? We went from 3 terms to now we have 4 terms. Why would I want 4 terms? Factor by grouping. Group the first 2, group the second 2. The first 2 have 1 in common. 12 and 3 is both divisible by 3, and they both have a z, leaving us with 4z plus 1. Negative 8 minus 2, they are both divisible by a negative 2, leaving us with 4z plus 1. Now that I have 2 terms, those 2 terms have 1 in common. 4z plus 1 times 3z minus 2. Is it right? You can always check it. 4 times 3, 12, z squared. 4 times 2 would be minus 8, plus 3 minus 2. And if you put all that together, you get what we started with. I'm going to take a second. If you're not liking this algebraic, you can take these 4 numbers, these 4 numbers that we had right here, and you can do it in an area model. So you may like this. Basically, you put the ax squared up here, so the 12z squared here. You put the c down here at the bottom right. So the ax squared is in the top left. The c is down here. And then these 2 numbers are what we use to split the z. What's kind of nifty about this is I can look across this row and go, what goes into 12 and 8? How about a 4 and a z? Down here, what goes into 3z minus 2? Nothing, so it'll just be plus 1. Another way of thinking about this too is to go 4z times what now? Gives me 12z squared. That would end up being a 3 and a z. Or if I look at the column, 12 and 3 are both divisible by 3. These both have a z. So it's really kind of a nice little system where there's a lot of double checks built into it. And last, negative 8 and negative 2, both divisible by minus 2. Notice the 2 groups that we have right here are our 2 groups right here. So if you like the area model, please feel free to do that, but you still need to write your answer as 4z plus 1 times 3z minus 2. Okay, last couple. This is where the AC gets a little trickier unless you catch something first. See, all my numbers here, I'll have a lot of people do 6 times 18 is, what is that, 108. Oh, buddy. Somebody else is going to go, look, I got a 6, a 3, and an 18. Those are all divisible by. Factor out those like terms first. Leaves us with 2a squared plus ab minus 6b squared. So now what's my a times c? 2 times negative 6 is negative 12. My b is 1. 2 things that multiply to make 12 combine to make 1. How about 3 and 4? Where the 3 is negative, the 4 is positive. What do we do with those numbers again? Split that middle term. So that 2a squared stays the same. This right here splits into a minus 3ab plus 4ab minus 6b squared. 4 terms, factor by grouping. First 2 have 1 in common. I think just an a, leaving us with 2a minus 3b. Second 2 have 1 in common, a 2 and a b, leaving us with, I need a little more room, I'm sure you can all just do this too. Alright, leaving us with 2a minus 3b. I actually really like this for me because this makes me feel like I've done something right. Look, make sure something's complicated here. I draw a line, sorry. Alright, because when I look at these two groups are the same. That makes me feel like I've done something right, because now I can factor out the 2a minus 3b, and that leaves us with a plus 2b. Wonderful. 18, 63, 27. Please don't do 18 times 27. Oh my goodness. Oh, by the way, this is not right, is it? Somebody caught me, I hope. Look, for it to be completely factored, do not forget to bring down a 3. In fact, when I pull something out like that, what I like to do sometimes is I'll kind of draw a line and go, don't forget to bring that down. Because our final answer still has that 3 doesn't just disappear. Okay? So 18, 63, and 27, I know that those are all divisible by 3. And they all have p's. In fact, how many p's in common? How about 2? That gives us 6, 21, and 9. Now, 6, 21, and 9 are still divisible by 3. That means we did not factor out the greatest common factor of those numbers. See, 18, 63, and 27, yes, I could pull out a 3, but this says 6, 21, and 9. I could have pulled out another 3, which means I really could have pulled out a 9. If you don't like that, just pull out another 3 and multiply it to the front, but I'm going to say, no, I should have pulled out a 9, which would have made that first number a 2, this a 7, and that one a 3 at the end. That is much nicer to deal with. Still complicated. How am I going to factor this? AC on the top, 2 times 3 is B on the bottom. What multiplies to make 6 combines to make 7. 1 and 6. Split the 7. So I have 2p squared plus p plus 6p plus 3. This 9p squared, don't forget to bring it down. Okay, what's the whole point of this? Keep in mind, this p plus 6p is still 7p. But by making it 4 terms, I'm setting it up for factoring by grouping. First group has a p in common, 2p plus 1. The second one has a 3 in common, 2p plus 1. So that now these two have what in common? 2p plus 1 times what's left, p plus 3. It's not done. That's why this arrow's here to remind me to make sure to bring down the 9p squared. So that's it. You can feel free to guess and check these to death if you'd like. I would encourage you to use the AC factoring. If you need some extra help, please feel free to come ask me about it. Come to the Learning Center. There's plenty of people that can help you. This is not going to be super easy, but it's not going to get much harder than this. So keep it up. So for section 6.5, we're going to be looking at some special factoring techniques. The good news is, if you already understand the rules for factoring, this isn't really anything, just kind of noticing some patterns. For instance, if I have something squared minus something squared, a squared minus b squared, okay? I can factor this by going first, look at the a squared. What multiplies to make a squared? Well, how about a times a? Second, this is kind of the term at the end, what multiplies to make b squared? Well, b times b. But our third step is to check the middle, and there is no middle term here, right? So it's almost like there's a 0 in the middle. There's nothing in the middle. So whatever I do, I need these b's to multiply to make a negative b, and I need them to 0 out in the middle. So what that does is that one b must be positive, and the other one must be negative, so that when they multiply, they'll make a negative, and so when they combine, they'll 0 out. Like, okay, does it work? Let's check it. A times a times b, that would be minus ab. B times a plus ab, and b times negative b squared. Notice we have the a squared at the beginning, the minus b squared at the end, and a positive ab and a negative ab would zero out. So I'm left with a squared minus b squared. So if I ever have a squared minus b squared, they call this a sum and difference. Basically, you can factor it to a times a, and a positive b, and a negative b. So let's practice that. X squared minus 49. Once again, don't check out your brain. Just look at this and go, okay, what would multiply to make x squared? Second, what would multiply to make 49? Well, 7 and 7. But to make it a negative 49, one would need to be positive, the other one would need to be, and verify that that 7 and negative 7 would make a 0 in the middle. If you're not sure, you can always distribute this. You would get x squared minus 7x plus 7x minus 49. We would get what we started with. So that would be our answer. What if I just have letters? What's y squared minus m squared? Not cool. Well, it still follows the pattern. It is something squared minus something squared. So first, what multiplies to make y squared? Second, what multiplies to make the m squared? Well, one positive m and one negative m. Does it work? You can always check it out. Y squared minus my plus my minus m squared. The my's cancel out, and so we do end up with what we started with. How about z squared minus 9/16? You're like, really? Okay, well, think about it. Still follow the same process. First, what multiplies to make z squared? Second, what multiplies to make 9/16? Well, that's not too bad. The way fractions work is I'm looking at the top times the top. What times itself makes a 9 on the top? And on the bottom and the bottom, what multiplies to make a 16? So 3/4 and 3/4 would make 9/16. And to cancel out in the middle, one would need to be positive and the other one negative. See? Nothing to be scared about. How about x squared minus 8? Well, what multiplies to make x squared? Second, what multiplies to make that 8? 1 and 8, 2 and 4. But none of those put a 0 in the middle, do they? So this is not factorable. Or we say it's already simplified, but not factorable, I think would be the way I'd want that. This doesn't factor any further. It doesn't fit the pattern of something squared minus something squared. But even if you don't see that, you can check it out, and nothing makes that 0 in the middle. How about p squared plus 16? You're like, I got this one. A lot of people will tell me p times p. That makes sense. Second, 16. How about 4 and 4? But here the 16 is positive. So to multiply and make a positive 16, both these 4's would need to be positive. Does that work? Does that make a 0 in the middle? If I have a positive 4 and a positive 4, that would be p squared plus 4p plus 4p plus 16. That is not a 0, is it? Like, well, that's easy. Just make them both negative. Okay, it makes these both negative. Does negative 4 and negative 4 cancel out? No. You're like, well, the only way that it could cancel out is if one of these 4's was positive and the other one was negative. But then look, that wouldn't multiply to make a positive 16. Now that would multiply to make a negative 16. What does that mean? This is not factorable. In fact, that's something I would put in your notes, that if I have a squared plus b squared, not a squared minus b squared, that is factorable, but if I have a squared plus b squared, that will always be not factorable. So we'll leave that once we get to that point. Let's kick it up a notch, just a little bit. 9m squared minus 64. Is this something squared? Minus something squared. Is this a squared minus b squared? Think of it this way. All right? What squared makes 9? What squared makes m squared? So 3m times 3m is 9m squared. That's our A. What times itself makes the 64? So it's plus 8 and minus 8. You're like, I don't know, does it even work? You can always check it. 9m squared minus 24 plus 24 minus 64. The middle this time zeroes out. How about 81 r to the 4th minus 16? I don't know. Think about it. Is there something squared that makes 81? Is there something squared, something times itself, that makes r to the 4th? Check that, right? 9r squared times itself gives us 81 r to the 4th. We have an A. What is our B? So we have two groups. 9r squared, and we have a plus 4 and a minus 4. Here's the problem. You type that in, you hit enter, it will say that this is incorrect. Well, I'm going to check it, and if you distributed it all out, it would turn back into that. You'd say, this computer is wrong, it made a mistake. No, it will say, look, there's something in here that's still factorable. This is still something squared, this is still something squared. Can we do a squared plus b squared? No, we said earlier that's not factorable. But look at the second group. That is a squared minus b squared. Is that factorable? Yes, it is. Then this can turn into two groups. What multiplies to make 9r squared? 3r and 3r. What multiplies to make the 4? A plus 2 and a minus 2. And the one that's not factorable, we bring down. So this is kind of a fun one because you did the regular a squared minus b squared, but you ended up with another a squared minus b squared that you had to factor. So be careful to check your answers and see if you can factor any further. This is not a squared minus b squared. Okay? And so I'm going to encourage you on these to kind of do this logical, and then we'll kind of get a form for this. But look, could you just do this logically? First, second, check. What they're wanting you to see is that this is an a squared, and this is a b squared. This is something squared, and this is something squared. So, what multiplies to make x squared? What multiplies to make 25? Well, there could be 1 and 25, or 5 and 5, but it's something squared. Wouldn't it be nice if it were just 5 and 5? Well, check it. Could 5 times 5 make 25? Yeah. Could it make a positive 10? Yeah, if they were both positive. So we're doing this logically, but basically, if I have something that is an a squared at the beginning, I believe this is actually a 2ab, then it will equal a plus b times a plus b, or a plus b squared. And if I have something that's a squared at the beginning and b squared at the end, but it's minus, this will become a minus b times a minus b, or a minus b squared. This is probably the one that I don't want you to memorize, okay? It really is a nice little trick, but you really just look for the patterns and still try to do this logically, because people that try to make this into a great magic trick, they end up applying this to everything and losing a lot of points. So let me show you what I mean. Is this something squared? Is this something squared? Then wouldn't it be great if this was one of our easy factors? Let's see. What squared makes 9m squared? What squared makes 16? But check, could I make a negative 24 out of those? Well, 3 times 4 is 12, and 3 times 4 is 12, but to make a negative 24, both those 4's would need to be, check it out. I get 9m squared minus 12m minus 12m plus 16. It works. I like the pattern. I definitely check it. If it has an a squared and a b squared at the beginning and b squared at the end, I always check the pattern, but also verify that it actually gives you the answer. Okay. The other option, and I'm not a huge fan of this, but I have had some people do this, is you could do AC factoring 9 times 16. 9 times 16 would be 144. I need two numbers that multiply to make 144, combine to make 24. How about 12 and 12? And so then you could split it, and then you could basically get to this answer anyway, 9m squared minus 12 minus 12. That gives me 3m minus 4. This one, factor out the 4, gives me 3m minus 4. So I end up with what? 3m minus 4 times 3m minus 4. That's a lot of work, but if you like AC factoring, you may like that better. But keep in mind, if there is a pattern, I would check it first. This one has a pattern. It's an a squared and a b squared. So wouldn't that be lovely if it factored nicely? What would multiply to make 25y squared? What would multiply to make 16? Don't just put this and circle it and move on. Check that that makes a 20. See, 5 times 4 is 20 and 5 times 4 is 20. This won't work, and here's why. This would give me 25y squared plus 20 plus 20 plus 16. That does not make that 20 in the middle. This didn't work. So you need to make sure you check these. If you're looking for a nice pattern, awesome, but go back and check and verify that you get the right answer. Okay? So what does that mean on this one? Well, what it really means in this situation is that this one will not be factorable. How would I verify that if I wanted to be 100% sure? You would have to do AC factoring. 25 times 16, oh my goodness, right? Would be 400. All the products of everything that multiplies to make 400. 3 doesn't go in, 4 does. 5 does. 6 does not, 7 does not, 8 does. 9 does not, 10 does. 11, 12, 13, 14, 15, 16, 17, 18, 19. So for section 6.6, what I'm going to do is I'm going to go through kind of a general notes for factoring. I'm going to tell you right now, this is gold. If there's something that you need to have on the test, this is it. You're going to be using factoring like crazy in Math 51, so I would encourage you again, have this down, save it for the next course. You use factoring all the time, okay? So first of all, we're going to factor out any like terms, okay? So make sure you put that as your first step. Always look for like terms first. Second, what we do is we go, how many terms are there? If there's 4 terms, 3 terms, or 2 terms, then we deal with it differently. 4 terms, we factor by grouping. Here's an example. 20k to the third plus 4k squared minus 40k minus 9. 2 groups. Group the first 2, group the second 2. The first 2 have what in common? A 4 and a k, leaving me with 5k squared and plus 1. The second 2, 45 and 9, since the leading coefficient's negative, factor out the 9, leaving us with 5. Oh, this should have been, oh, I'm supposed to pull out 2 k's, which makes that just k. Okay, so 4k squared, 5k plus 1, minus 9 leaves us with 5k plus 1. So, now, what's the purpose of this? These 2 groups have what in common? 5k plus 1 times 4k squared minus 9. That's factoring by grouping. Do verify that 4k squared minus 9 does factor further, so this is actually a really good example of just verifying. This is a binomial, this is a binomial. We should have just had that section. So what ends up happening is 4k squared minus 9 becomes 2k plus 3, 2k minus 3, and then bring up the 5k plus 1. So this is a really good example because it just reminds us that what? This can still be factored. So make sure that you verify those. Second, if I have 3 terms, you can do a mental math, or they call it guess and check, but I go first. What multiplies to make x squared? Second, what multiplies to make that 3 combines to make a 2? About a 1 and a 3. To make a negative 2, the 1 would need to be positive, the 3 would need to be negative. And it is really that easy. What happens if the a is not a 1? Well, it gets a little more complicated. I recommend AC factoring. I like to use the table. Some of you like the x, some of you like the area model. All are fine. But I've already set this one up, so 5x squared minus 13x plus 6. 5 times 6 is 30. That's my AC. I want to make a 13. How about 3 and 10? 2 and 15 might work too, but the issue here is what? If I do 15 minus 2, if I do 3 and 10, I am not sure what the issue is. Let's try the 2 and the 15 first. So 5x squared, if I did plus 2 minus 15 plus 6. Yeah, I'm actually just curious what would happen here. So these have an x in common, leaving us with 5x plus 2. And these have a 3 in common, leaves us with 5x minus 2. That doesn't work, because these 5x plus 2 and 5x minus 2 are the same. So the 2 and the 15 don't work. I'm just making sure that I'm not lying to you before I do this. Yeah, no, this didn't work. Okay, that's okay, so just try it. The 2 and 15 doesn't work. There is another option. Instead of 2 and 15, we could use minus 3 and minus 10. Another way of thinking about this, I think, is that these need to be the same because I need them to multiply to make a positive at the end. But if you, like I said, if you didn't see it, you could have checked the other one. These two have 1 in common, x leaving us with 5x minus 3. These two have a minus 2 in common, leaving us with 5x minus 3. So now the two groups have 1 in common, 5x minus 3 times x minus 2. Alright, so that's the example. Like I said, you don't have to stick the examples. You could just have the factoring notes, but I like to just put an example next to each one. So if there's one that's harder for you, then have an example on your note card next to it. Okay. Basically, what did we do? We went from 3 terms to 4 terms. Why did we want to split this middle term? Well, when it's 4 terms, I can factor by grouping, and it's a lot easier. Okay. So that's really my favorite approach when the a is not a 1, is to use that AC method. Factor by grouping. What if it's a squared minus b squared? A minus b times a plus b. So x squared minus 9 is x times x plus 3 minus 3. What if it's a squared plus b squared? Well, we said that does not factor, so don't do it. It's a trap, right? But what if it's a cubed minus b cubed, or a cubed plus b cubed? That does work. X cubed minus 27, the first group stays the same, so x minus 3. And then it's x squared, opposite, plus x times 3, 3x. Always positive, plus b squared. 3 squared is 9. What if it's a plus? This one is factorable. A plus b, so x plus 3. A squared, x squared, minus AB, minus 3x, always positive, plus b squared is 9. So, I mean, I'd be able to factor the more complicated ones of those in the homework, but on the test, you know, maybe something at this level, nothing too crazy. Really is a Math 51 issue, okay? If you have those notes, you are ready. Those are all the notes you need for 6.6. All we're going to do is go through them and check them. First, is this ready to be factored? Well, yeah. Some people will look at this and go, oh, it's a trinomial. What's the first thing we should look at first? Any like terms. 6, 3, and 63 are all divisible by 3, and they also all have a x. What does that leave us with? 2x squared minus x minus 21. What does this do for me? Some people will guess and check this to death. Please feel free, but I like AC. What is 2 times 21? About negative 42. I just used the table. If you want to put it in the x, you can. But I'm looking for things that make negative 42 and combine to make a 1. 1 and 42 won't. 2 and 21 won't. 3 and 14 won't. 4 doesn't go in. 5 doesn't go in. But 6 and 7. 6 and 7 if it's a positive 6 and a negative 7. Split it. Be careful here because this 3x, a lot of people will lose it. So I would just draw an arrow to remember to bring it down at the end. So we now have 2x squared. We said plus 6x minus 7x minus 21. Why did I want to turn that into 4 terms? Factor by. Grouping, the first two have 1 in common, 2 and 6 by 2. They both share an x, leaving us with x plus 3. When this leading coefficient is negative, make sure to factor out not just the 7, but the negative, so that we're left with x plus 3. And now, what do these two terms have in common? X plus 3 leaves 2x minus 7. Why do I have this arrow over here? Oh yeah, don't forget to bring down the 3x. This section is nothing new. It just takes what you've done, puts it together, and you'll see, kicks it up a notch. Next example already has 4 terms. 4 terms, factor by. Group the first 2, group the second 2. 20 and 4 are both divisible by 4. Do not forget to bring out the k squared. That leaves us with 5k plus 1. Negative 45 minus 9, pull out the negative, and the 9 leaves us with 5k plus 1. These two groups have 1 in common, 5k plus 1. And if we pull that out, that leaves us with 4k squared minus 9. It is so tempting to be done, right? But what I'm left with is a binomial, and one of these is a squared minus b squared. So you have to continue to factor that. What multiplies to make 4k squared is 2k and 2k, minus 3 and plus 3 to 0 out in the middle, and don't forget to bring down the 5k plus 1. Now factored completely. Okay. Notice that was also the example that I put on the notes. I think this is a great example because it merges them. But be comfortable factoring by grouping. This is a mess. A mess with how many terms? 1, 2, 3, 4. If I look at my notes, 4 terms says factor by. Grouping. Pull out. These two have 1 in common. Think just a p. Leaving us with p squared minus 2q squared. These have what in common? Looks like just a q. Leaves us with p squared minus 2q squared. These have what in common? P squared minus 2q squared. And if I factor that out, that leaves me with p plus q. Now this is tempting to look at this and go, ooh, that's something squared minus something squared, but that 2 kind of jacked us up. So this actually doesn't factor any further. I encourage you to check it, but right, you're going to end up going, what times itself makes 2? If it's not a pretty number, and that one's not, then we leave it. This is factored completely. Don't do this. I'll have some people do this, and then they'll write not factorable. That's a little irritating because, first of all, it's a damn lie. You factored something, right? You literally factored something out. It's no longer factorable past that, but the answer is not that it's not factorable. The answer is this, where you factored something out. Okay, let's practice some. So in section 6.7, we're not going to just be playing with quadratic expressions and factoring them and combining like terms. We're actually going to be able to solve quadratic equations using those skills. So here's the argument, and you want to write this down. Basically, if I have a, that almost looks like minus, if I have a times b equals 0, then I have two things that multiply to make 0. Well, then one of them must be 0. Either a is 0 or b is 0. In either situation, the whole equation would equal 0. One must be true. Either a is 0 or b is 0, or both could be 0. This is called the zero product property. Okay? So we're going to use this same logic right here, that two things that multiply to make 0, one of them must be 0, or if one of them is 0, the whole thing becomes 0. And I'm going to look at this, because this is not two things that are being multiplied. X squared plus 5x plus 6 equals 0 is not something where there's two things being multiplied, but it can be. See, we can factor it. If this factors, it will factor into two groups that are being multiplied. First, what makes x squared is x and x. Second, what multiplies to make the 6 combines to make the 5. 1 and 6, 2 and 5, since they both need to be positive, I'm thinking 1 and 6, 2 and 3, I'm thinking it's the 2 and the 3. Both positive to make the positive 5, both positive to multiply to make the positive 6. So this is factored, it must be factored, set equal to 0. And once it's factored, there's that zero product property again. What makes this 0 is if this first group, if x plus 2 equals 0, then the whole thing would become 0. Or if x plus 3 equals 0. Well, set each group equal to 0 and solve it. If I solve this one on the left, we subtract to get that x is equal to about negative 2. If I subtract the 3 right here, we get that x is equal to a negative 3. That's our solutions, negative 2 and negative 3. See, I can solve this even though there's two x's here, because when I put it into two groups that are being factored, I can figure out what makes each group 0, and those are our solutions for the original equation. You can always check this, and I encourage you to do this. We just said negative 2 is a solution. If x equals negative 2, then I'm going to go up here to the equation, and everywhere there's an x, I'm going to put a negative 2. So x squared becomes negative 2 squared plus 5 times x, negative 2, plus 6. Let's see what this becomes. This should equal 0. This becomes 4 minus 10 plus 6. This gives us 0 equals 0. This is one of our solutions. We also said that negative 3 was a solution. Well, let's check it. Negative 3 squared plus 5 times negative 3 plus 6. Remember, we're putting these numbers in place of all the x's in the equation. So what do we get here? Looks like 9, negative 15, plus 6. Well, that's cool because what? 0 equals 0. These are our two solutions. These are the solutions that work both when it's factored and when I plug it into the original equation. Okay? All right, let's keep going. The good news is this. This is actually one of the more advanced questions. You're going to see a lot of the homework is going to start off more like this. And you're like, well, that looks scarier than what we just did. Well, not really, because the first step's already done. See, I want it factored and set equal to 0. So that's already done. So what do we do when it's factored and set equal to 0? We take each group, and set them equal to 0. What do I do with this x right here? See, a lot of people just ignore it. And that's not going to work because what we're going to say here is that one of our solutions, if I set that group equal to 0, that is a solution. X equals 0. If I stick a 0 right here, I get 0 times 1 times negative 7. The whole thing zeroes out. 0 times, I don't really care, but 1 times negative 7, it equals 0. Take the second group and set it equal to 0 and solve it. So we're going to subtract the 1. 5x is equal to negative 1. Divide by 5. And x is equal to negative 1/5. I'll just leave it. There. Is it right? Well, let's check. I get negative 1/5 times, well, negative 1/5 times 5 gives us negative 1 plus 1. And over here I have negative 1/5 minus 7. Oh, see, after you said, I told you this looks harder, but look, what happens here in the middle? What is negative 1 plus 1? That becomes a 0. Doesn't matter what anything else is at that point. because anything times 0, the whole thing zeroes out. Negative 1/5 works. And the last one's not difficult. X minus 7 equals 0. So when I add x equals 7, is it right? Well, I get what? 7 times 35 plus 1, big messy numbers, times 0. All this other stuff doesn't matter. The whole thing zeroes out because that last group. These are our 3 answers. Like I said, the most common mistake, the thing you want to kind of put a star on to remember, is that if you have an x by itself, that is still a solution. You set that group, that x, equal to 0 to get that solution. This one is not factored, unfortunately. And what makes me a little sad is I'll have some people look at this and tell me it can't be factored. Or they'll try to put it in 2 groups, or they'll try, and I'm going to say again, you really need the sections 5.1 through, or 6.1 through 6.5 strong on this, so that you know how to factor. The first thing I always look for when I factor is any like terms. 3x, 21, 3 and 21 are both divisible by 3, and these both have a x. When I factor that out, I'm left with x plus 7. This is now factored. Take each group, set it equal to 0. You can treat the 3x like a group if you'd like, or you could do it separately. It makes more sense, I think, to group it. 3x equals 0, and x plus 7 equals 0. The one on the left, don't be scared of that. First of all, do not do this. We should be past this. 3x minus 3. The 3's don't cancel. You cannot cancel multiplication with subtraction. We divide and get that x is 0. And x is negative 7. And what I love about this chapter is we can check it. Look, what is 3 times 0 squared plus 21 times 0? What is 0 plus 0? See, that 0 is one of our solutions. What if I put in a 7? This one's not going to be as pretty. It's going to be 3 times negative 7 squared plus 21 times negative 7. Ooh. 3 times 49 plus, what is that? 140 minus negative 147. 3 times 49 is positive 147 minus 147. We get 0 equals 0. Those are our 2 solutions. On example 4, here's the temptation. This is the common mistake. This is wrong. People go, oh, this is like the other one, and just factor out the x. X minus 8 equals 16, and start just setting groups equal to what? Well, remember, this is wrong because it needed to be set equal to 0, and this is not set equal to 0. So do not do this. You need this set equal to 0 first. You need that 16 to be a 0. We can do that. To undo a negative 16, we add 16. So that we have x squared minus 8x plus 16. Can this be factored? I sure hope so. First, the x squared is x times x. Second, what multiplies to make 16 combines to make an 8. How about 4 and 4? And to make a negative 8, both those 4's would need to be negative. Set each group equal to 0. X minus 4 equals 0. X minus 4 equals 0. That's weird. We get x equals 4. We get x equals 4. This is just called a double solution. We got the solution twice. Our answer is only x equals 4. How do I know that? Well, I could check it. Does x equal 4? What's 4 squared minus 8 times 4? Well, if we're right, it should equal negative 16. What is 16 minus 32? Negative 16 equals negative 16. This is our solution. Next one, you're like, I'm not going to fall for it this time. This is not set equal to 0. Okay, that's fine. Then let's move the 25. So I have 4t squared minus 25 equal to 0. Can this factor? Well, I hope we just got done with the section a couple sections ago of special products. This has two terms, so my notes tell me to look at binomials. This is a squared minus b squared. This is what times itself makes 4t squared. What times itself makes 25. But I need it to combine to make a 0 in the middle. So one of these 5's is positive and one of them is negative. So we have it set equal to 0. We have it factored. Now we take each group and set them equal to 0. For the first one, we subtract the 5, so that 2t equals negative 5. We divide to get negative 5 halves. The second one, we add the 5 to get that 2t is equal to 5. We divide to get positive 5 halves. So t is equal to 5 halves. T is equal to negative 5 halves. By the way, this is not the way I would have solved this. There's nothing wrong with this method, but let me show you something else. See, 4t squared equals 25. This is different than some of the previous ones because we only have one t. That t, I don't have ax squared plus bx plus c. I just have that single t. And if I think about PEMDAS, because we've solved using inverse operations before, that t is being squared. It's an exponent, and it's being multiplied. So if I want to do inverse, we do the opposite and backwards. So we undo the multiplying by dividing. T squared is equal to 25 over 4. And we undo the exponent. We undo a second power with a second root. So that we get t is equal to the square root of 25 is 5. The square root of 4 is 2. But you have to remember, if you want to do it this way, there's nothing wrong with it, but you have to remember that from the square root, we get a plus or a minus. So I still get positive 5 halves and negative 5 halves. If that's confusing to you, don't do that. They're not really intending you to do that at this point. I'm just telling you how I would handle this question. Okay? Last but not least, and I'm going to tell you right now that this is not my favorite example. They're in the homework. They're a bit of a challenge. The issue here is what, again? This is not set equal to 0. But I can't just subtract the 9 over because the left side's all complicated. So what they're going to make you do here is you're going to need to clear up the left side, distribute it out. X times 2x, x times negative 1, 3 times 2x, and 3 times negative 1. Now I can combine the like terms. Negative 1 plus 6 is, I think, positive 5. And now I can set it equal to 0 and get 2x squared plus 5x minus 12 equals 0. This we have solved before. This is where the a is not a 1. So how do I factor this? You're either going to use this diamond or you're going to use the t. But either way, I like to call it a c factoring. What is 2 times negative 12? And our b goes down here is the 5. We're looking for two numbers that multiply to make 24, combine to make 5. If you're not sure, list them out. I see a 5 right here. The 3 would need to be negative. The 8 would need to be positive. I use those two numbers again, just like we had before, to take the middle term and split it. Why do I want 4 terms? To factor by. factor this out of these two. They have, I think, only an x in common, leaving us with 2x minus 3. The second one, I think they have 8 and 12 is divisible by 4, leaving us with 2x minus 3. This is lovely because these two terms have what in common? And when I factor that out, I'm left with the x plus 4. All this work, like I said, this is a way harder question than I would give you on the test. There are a couple in the homework. You know, stick around and get some help on these. I expect these to be a little more difficult. This might be one you need a little more help on. I think it's kind of adding punishment where it's not necessary. But anyway, let's go ahead and finish this up. So now that we have our two groups, to solve them, set each one equal to 0. Set each one equal to 0. See, this makes me sad. I will have some people just circle this like it's the answer. That's somebody that didn't finish the homework for this chapter. It's kind of sad. But basically, this is not a solution. To solve, we have to set each of those groups equal to 0. If you stop at this point, I'm going to end up giving you half credit, because you have done all the work, but you have yet to actually solve it. Set each group equal to 0. Start solving. Now we earned another quarter point. And now we earned full credit. There should be two answers, x equals 3/2, x equals -4. And for the last time, could I check that here? Yes. Do I want to plug it into this here? No, probably not. What I would probably do is I would use some technology to plug those in. Just put that in place of the x's and hit enter, and it should be 9. The -4, plug it in. But the idea is you could still plug these numbers in. If it's a homework question, go ahead and type it in, hit enter. If it's wrong, rework it. But on the test, the reason I love these questions is you can always check these answers.